Okay, welcome back to our section 1.1 lecture. We're going to be talking a little bit now about how we can improve our previous estimates. So in the previous video, we talked a little bit about how we can kind of try to estimate this thing called area underneath the curve, where we're taking some random function. In this case, ours is this function here. We're calling it f of x for the moment, and our goal is to come up with some way of computing, or at least even defining, this area here that lies between the curve itself and the x-axis. So we're trying to approach this problem by saying, well, we don't really know how to do this right now, but we do know how to compute the areas of rectangles. So let's try to find some different rectangles that we can use to approximate this area. And so we had 4 different reasonable rectangles that we could construct. We had a left endpoint rectangle. So if we're working with some x values a and b here, then we wanted to, we established that the base of our rectangle needed to be of length b minus a. But the height of our rectangle was sort of variable. That was the thing that we were considering changing. So on the one hand, we chose the y value for the point on the far left as the height of our rectangle. So in this case, that was f of a. Another approach that we had was to use the y value on the right, and that was f of b. Another approach that we had was using the largest y value, and we didn't know exactly what x value would create that largest y value, so we called that x upper star. And similarly, we could also use the smallest y value as the height of our rectangle, and we could call that corresponding x value x lower star. So we have all of these formulas for areas, but we want to certainly do better. These aren't great formulas by any means. And so what we can do is we can say, well, instead of drawing one rectangle, what if we drew 2? So we're still in the case where we have some function here, which we're calling y equals f of x. And we have our left endpoint of our interval will be a, the right endpoint of our interval will be b. And maybe what we want to do is we want to insert some intermediate x value here. Maybe we'll put it right there. But right now, we kind of maybe have this idea that we're going to be doing this process a lot. We're going to go from 2 rectangles to 3 rectangles to 4 rectangles and so on. And so we want slightly better notation that's going to allow us to do this process some more. So I'm going to, instead of calling the left endpoint a, I'm also going to call it x0. And these are the same number. We're just having 2 different names for it because I'm going to want to call this middle point here x1 and the right point x2. So you can guess this is going to work nicely with our sigma notation that we're going to want to introduce later as we're doing this process. So let's see. So now what we want to do is we want to do 2 different rectangles. One of those rectangles is going to be between x0 and x1. The other rectangle is going to be between x1 and x2. And so we have, again, the same kind of 4 options that we had previously. We have a left endpoint option, we have a right endpoint option, we have an upper option, and a lower option. So let's sort of explore what those different things look like here. So starting if we're thinking about making the heights of each of these 2 rectangles that we're going to draw equal to the y values of the left endpoint, I'm going to need to start by looking at my first rectangle here, which is going to be here from x0 to x1. And I'm going to want to make the y value, or the height of this rectangle, equal to the height of the left endpoint here. So that rectangle is going to look something like this. And I'm going to draw this horizontal line all the way over until I get to the x value x1. So my left rectangle here looks something like this, and my approximate area is going to be this green area that I'm shading in underneath this rectangle here. Cool, so here's one of my rectangles, but my other rectangle needs to lie on the interval between x1 and x2 here. So again, I'm doing this left endpoint approximation, and the left endpoint of my new interval here is at x1. So what I need to do is I need to find the y value at x1, and again, I need to draw kind of this dashed line over until I get to the next point, this x2 here. So I here come up with a new approximation for my area. And we can see that this does a little bit better job of conforming to the curve than our previous estimate did. So with these two rectangles, I'm accounting for the fact that I have a little bit of a peak here and a little bit of a valley here, since my y value of my left endpoint is a little bit lower than the y value on the right rectangle. If we in fact go back to the previous side, we see that there's a lot of missing area in this region that our green didn't account for, and our two rectangle approximation does pick up some of that area. Certainly not all of it, but it's a start at least. So if we want to write down a formula for this approximate area here, we would say, well, we've got two rectangles now, so we're going to need to add up the areas of these two rectangles. The area of my green rectangle is going to be base times height. We know that the base has length x1 minus x0, since I've set it up to be this rectangle here. The height of this rectangle I determined by the left endpoint here. And so the height is going to be f of x0. But now we need to account for our right rectangle here. And so I'm going to look at the base here, and this base has length x2 minus x1. And its height is equal to the y value of the left endpoint of the red rectangle. The left endpoint of the red rectangle is this the y value on the curve at the value x1. And so the height here is going to be f of x1. So the entire area that I'm working with right now with this two rectangle left approximation is exactly going to be this x1 minus x0 times f of x0 plus x2 minus x1 times f of x1. In fact, if I set this up in kind of a nice way, maybe I want to set this up so that x1 is in the middle of a and b. If I do that, then I know exactly how far, how long this distance is and how long this distance is, because it's half of the distance between A and B. And so I can rewrite my formula here with a little bit more detail. This x1 minus x0 quantity is going to be b minus a over 2. I'm still going to write f of x0. And this x2 minus x1 quantity is also b minus a over 2 times f of x1. So we have kind of a nice formula here that is going to tell us how to approximate this area. Again, it shares similar advantages and disadvantages to the left endpoint approximation with one rectangle. This is a very nice formula. It was pretty easy for us to write down. It only involves our choice of A and B essentially, since x0 is A, and x1 is the average of A and B. So very easy to compute. The problem is we don't really know how this compares to the actual area under the curve, that original purple area that we were trying to approximate. So let's talk about maybe what the right endpoint approximation would look like. We have a very similar setup. We have A and B, which we're again going to be calling x0 and x2. The middle point is going to be x1 here, and again, that's going to be in the middle. And now what we need to do is, in order to make our right endpoint approximation, we want to look at this first rectangle, or this first kind of base of our rectangle, and we want to find the y value at the right endpoint. So okay, so that tracing it up here and over here, and we have let's see, let's make this area green. So I've now taken this first rectangle, I've taken that right endpoint approximation. For this second rectangle between x1 and x2, I'm going to again use the y value on the right, and that's going to be the height of my rectangle. and we can shade that in red. So this one looks a little bit funnier. Certainly there's a large amount of area that we're missing here, and maybe some extra area that we have here. So the left endpoint happens to work out a little bit better for this particular function, but certainly for other functions, maybe the left endpoint, or maybe the right endpoint would be better than the left endpoint. And certainly it's not the case that left endpoint is always better than right endpoint. So anyways, so if we want to now compute our area in terms of some of the quantities that we have here, then our area of our green rectangle, well, the base is still going to be that x1 minus x0, and the height is going to be the height of the right endpoint this time, so that's f of x1. To that, I am adding, let's see, the height of, or the base of the right rectangle is going to be x2 minus x1. And its height is again the height of, is the y value of the rightmost point, and so that is going to be f of x2. And so if I want to, again, think about the fact that x1 is in the middle, I know that I can rewrite this as, let's get that in our usual color scheme. So this is now going to be x1 minus x0, that distance is b minus a over 2 times f of x1. And the distance or the base of the right rectangle is x2 minus x1, which is also b minus a over 2, f of x2. Great, so we have some formulas for some right and left endpoint approximations with two rectangles now. Great, all right, so let's do our analogs for our lower and our upper approximations. So we want to think about definitely doing an overestimate now, but again, we're going to split it up into two rectangles. So we have x0, we have an x1, we have an x2. And now what I'm going to do is, again, kind of find the, if I want to do an upper approximation, I want to find the largest y value between x0 and x1. So just kind of blocking off that, if I'm looking at this section here, I can see that the largest y value actually occurs at the right endpoint. So I'm going to take the right endpoint as the height of this rectangle that I'm going to be drawing. So let's go ahead and find that. And the left rectangle here, as usual, we will shade green. Now what I want to do for my upper approximation is now search on the right half of the interval here. So I want to find the largest y value among all of these y values. And this largest y value doesn't occur at one of the endpoints. It, in fact, occurs right here in the middle. And so what we're going to do is we're going to take this y value as the height of our rectangle and compute its area. So we can see now that this, in fact, does a better job of approximating the area than our previous upper estimate did. Our previous upper estimate didn't allow us to bring this rectangle down any lower. We were forced to use this height of the rectangle for the entire interval, whereas right now, we can, with two rectangles, we can reduce the height of one of the halves of the rectangles that we're dealing with. So again, we're kind of faced with this problem, though, of what exactly is this x value. And also, I mean, I guess right now we have a name for this x value, but maybe the maximum didn't occur at one of the endpoints. Maybe it occurred in the middle. So we need to give ourselves some new names. So maybe I would call the x value which maximizes f on this first interval, maybe I can call that x1 upper star. And maybe for the x value in the second interval, which maximizes f, I can call that x2 upper star. So now when I'm writing out a formula for the area here, I get that the area is going to be the green area plus the red area. So again, the base of the green rectangle is going to be that b minus a over 2. And its height now is f of x1 upper star. For the red rectangle, again, its base is going to be b minus a over 2, and its height is now going to be f of x2 upper star. All right, last but not least, we want to think about doing a lower approximation. So this time, instead of taking our x values which maximize f, or instead of taking our largest y values, we want to think about x values which minimize f. So we want to get an underestimate for our area here. And in order to do this, let's see, we need to first focus on this subinterval here. So we want to find the smallest y value among these, and we can see that that occurs right here at the valley. And so let's see, so let's give that guy a name. That's going to be called x1 lower star, meaning the x value which minimizes f in the first subinterval. And so its height, well, let's see, we can draw that rectangle now. And shade it in. And on the second interval, we want to think about, well, where's my lowest y value here? And it looks to me like it's at this endpoint here, so we're going to go ahead and say that. And we want to use that as the height of our rectangle on the right rectangle here. Cool. So now again, you can see we have an underestimate for our area, but it's a better underestimate than we had before. And if we want a formula for this area, we can write it down as b minus a over 2 for the base of our green rectangle. And its height is going to be the y value of x1 lower star, so f1 x lower star, or f of x1 lower star. There we go. For the second rectangle, again, we're going to have the base being this length b minus a over 2, and its height is going to be f of, we should call again, the minimizing value, we should give it a lower star, so this is going to be called b and x2 and x1 lower, or x2 lower star. So we have f of x2 lower star there. All right, great. So I think that's where we're going to pause this video for the moment. We've done 2 rectangles. Maybe think on your own about the next page here and think about doing 3 rectangles. Think about what that might look like. In the next video, we'll go ahead and cover that. But for the moment, we have a nice setup for our formula here for actually computing some of these areas and getting better approximations.